Hello everyone, welcome again to ETEC221 lectures. In today's lecture 2, we will talk about practical design of digital to analog converters and their properties. Digital to analog conversion involves translation of digital information into equivalent analog information, and this is accomplished by the use of digital to analog converter or DAC. DACs are used whenever the output of a digital circuit has to provide an analog voltage or current to drive an analog device. As an example, the output from a digital system might be converted into an analog control signal for adjusting the motor speed, or the furnace temperature, or for controlling almost any physical variable. Computers can be programmed to generate the analog signals through a DAC required for testing analog circuitry. A digital to analog converter, or DAC, is sometimes considered as a decoding device. Digital to analog conversion is a straightforward process and is considerably easier than analog to digital conversion. In fact, DACs are used as components in some analog to digital converters. So that's the reason that we will consider digital to analog conversion first. We will analyze few different types of DACs, like a weighted resistor DAC, R2R network switch voltage source DAC, R2R network switched current source DAC, and switched capacitor DAC. Before we proceed with the explanation of operation of weighted resistor DAC, let us do a quick review of a summing amplifier that was covered in ETEC221. A summing amplifier has two or more inputs, and its output voltage is proportional to the negative of the algebraic sum of its input voltages. A two-input summing amplifier is shown in the figure below, but any number of inputs can be used. The operation of the circuit and derivation of the output expressions are as follows. Two input voltages VIN1 and VIN2 are applied to the inputs and produce currents I1 and I2 as shown. Now let me remind you that because of this very small differential voltage at the input, the potential at the inverting terminal is very close to ground, to zero. So that's why we call it virtual ground. And because the input impedance of the op-amp is very, very high, then the current flowing into the op-amp will be very small compared to the sum of currents I1 and I2. That tells us that the current IT will flow through resistor RF, making voltage drop across it. Now, if we apply Kirchhoff voltage law around the output loop, which includes Vout and voltage drop RFIT across the resistor RF, then we can find the expression for the output voltage to be negative IT RF. Substituting currents I1 and I2 in this expression using simple Ohm's law, I1 becomes VI1 over R1 and I2 becomes VIN2 over R2. This is the expression which indicates that the output voltage is proportional to the sum of the input voltages. Now, careful selection of resistors R1, R2, and RF can make a different arrangements of that sum. But if they are all equal, then the Vout becomes a simple sum of the two input signals. Of course, negative sign indicates inversion because that's, as you can see, typical inverting amplifier. The weighted resistor DAC shown is based on summing amplifier. The number of rungs in resistive network corresponds to DAC resolution, or number of bits, and in this particular case it's a 4-bit configuration. Operators D0 to D3 represents binary input. When value 0 or low has been assigned to operator Corresponding rung is connected to ground, 0 volts ideally. Contrary, when value 1 is assigned, corresponding rung is connected to reference voltage EREF. In reality, these switches are replaced by outputs from microcontroller or any other logic controller. Pay attention to resistor values in the rungs. The most significant bit has a base value of R, and then each subsequent rung will have resistance twice the value of the preceding rung. In 4-bit DAC, LSB rung will have 8R resistance. One can tell right away that D0 rung, when switched to EREF, will make the smallest contribution to output voltage, while the most significant bit rung contribute the most. Therefore, contributions are weighted depending on bit position. The main disadvantage of rather simple DAC is selection of binary distributed resistors, especially in case of high resolution. So the total output voltage can be expressed in the case of a 4-bit DAC with this expression, where D3, D2, D1 and D0 operators actually are getting either value 0 or 1 depending on the actual word that is converted to analog voltage. In practical cases, RF is usually equal to R, so this ratio is 1 and we have a simple sum of all weighted sources EREF. Now, for instance, if we are interested in finding output voltage for the input word 0110, that means the operator D3 will have a value of 0, then operator D2 1, D1 will have a value of 1, and the least significant bit will have D0 will have a value of 0. Multiply with total reference voltage, which is assumed to be 5 volts, will give us final result. Of course, once again, keep in mind that all values are inverted. They have a negative sign because it's an inverting amplifier configuration. The main disadvantage of a rather simple DAC like this one is a selection of binary distributed resistors, especially in case of high resolution. Some digital-to-analog converters utilize a series parallel resistive network called R2R. Those are made of two resistance values only, which is R and 2R, so it is much easier to build them. Illustrated schematic shows that all horizontal branches will have a value of R, this one, and this one, while the vertical branches will have a value of 2R. R2R networks, which are terminated by 2R resistor, that would be 2R resistor, have one very interesting property. When looking back into the network from any vertical branch, either A, B, C, or D, we find equivalent resistance to be the same, and it's equal to R. For instance, let's find total equivalent resistance looking back into the circuit from point B and common. When you are looking for the equivalent resistance, you start on the opposite side and you find that 2R and 2R are in parallel, which gives you R value. R value will be in series with this resistor R, making 2R and 2R in parallel again, which of course gives total equivalent resistance of R. Setting different rungs will result in the same value. Of course, if none of the vertical rungs are connected to reference voltage Vref, the output voltage must be 0. However, if one or more rungs are connected to Vref, there will be some output voltage whose value depends on weighted rung containing reference voltage. To find actual output voltage, we can use Thevenin's theorem as illustrated here. Say that the rung D2 is connected to reference voltage Vref. Then the whole linear network at point C in rectangular area can be substituted by only one source, ETH, representing voltage between point C and common, of course with the right-hand portion of the circuit disconnected. This source will have a series resistance of RTH looking back from point C with the removed EREF from the circuit. Now, with this simplification, by replacing the whole network with equivalent source ETH and series resistance, it is quite easy now to calculate voltage Vout, which is voltage between point D and common, using this voltage divider. Here we have a detail about the Thevenin's equivalence finding. In the first step, we are finding total equivalent resistance, looking back into the network. For this purpose, the source Vref must be removed from the C branch. In this case, we have a simple terminated R2R network, which will give us total equivalent resistance of R. If we want to find the voltage of a Thevenin's equivalent source, it's a voltage between point C and the common, so it's a potential at the point C. Leftover circuit from point B can be replaced with the equivalent resistance R. So obviously voltage that we are looking for is voltage across sum of those two resistors R and R. Using voltage divider, we can easily find that this voltage is given as 2R, that's R plus R, over 2R, R plus R, plus resistance in the C branch, which is 2R, multiplied with the total applied voltage, which is EREF. Now, with this substitution with the Thevenin's equivalent, our original circuit is reduced to a simple voltage divider circuit. We will find output voltage as a potential at the point D, and as you can see, that's the voltage across resistor 2R in D3 rang. So our expression for output voltage will be 2R over 2R plus 2R multiplied with total applied voltage. This time it's ETH. ETH is related to Vref with this expression, so substituting expression for ETH, we will get final expression 1 over 2 to the power 2 Vref. Now, in this example, position I, which is number 2, is the bit position of the second most significant rung connected to Vref. So as you can see, I designate the bits position. It goes from 0 to n minus 1, where n is the total number of bits available, in this case 4. With the introduction of I as a bit position, we can use a recursive formula to express the same value. Here, once again, n is the total number of bits. I is a bit position in a rank that is connected to vref. So n is 4, I is 2, 2 to the power 4 minus 2 is 2. So we were getting the same expression, but it's convenient because it tells us what will be the contribution of each of the ranks connected to vref by defining bit position I. Here is example of the switch voltage source digital analog converter, of course 4-bit version. Same DAC we will investigate in our lab exercise. Actually, that's identical schematic that students will build. You recognize R2R network, and you have 4 operators or 4 switches which can connect each of those vertical branches either to common, as illustrated here, or in opposite position you can connect reference voltage designated here as E-ref. By doing that, you can set up any digital input word. We already found that if only one input, I say, is turned on, that means corresponding switch connected to E-ref, the contribution of that particular bit position will be E-ref over 2 to the power n minus I. N is total number of bits. Here is 4, and I is the current bit position which is connected to E-ref. To find the output voltage which corresponds to arbitrary input combination, that means that several inputs or all of them can at the same time be connected to high, we can use the principle of superposition. Simply add the voltages produced by the inputs with digital ones as if they are acting alone in the network. Typical values for R and 2 are around 10 kiloohms and 20 kiloohms. The problem is they have to be identical, so it's good that students actually measure the values and exchange the resistors in such a way that they can achieve perfect or the best possible match of the values. For accurate conversion, the output voltage from the R2R ladder should be connected to high impedance to prevent loading effect. Normally it should be an operational amplifier in voltage follower configuration as shown in figure. As you can see, it's a buffer or non-inverting application with a gain of 1. By doing this, input impedance that is attached now to R2R network will be extremely high, and it will not influence distribution of the voltages in the network. This type of analog digital converters is referred to as switched voltage source converters because we are switching in and out this reference source E-ref. When binary input goes high, the reference voltage is effectively switched into the circuit where it is summed with the other input voltages. For any combination of digital inputs, we can use superposition principle, as already stated here, and find total output voltage, which is sum for all I from 0 to n minus 1. That means that the sum includes all digital inputs DI switched on. The digital input that are switched off will not contribute to the output voltage. With the modern technology used to construct integrated circuit DACs, currents can be switched in and out of the circuit faster than voltages can. This is the reason that most integrated circuits, digital to analog converter, utilize some form of current switching. The binary inputs are used to open and close electronic switches which connect or disconnect internally generated currents. These currents are weighted according to the bit position they represent and are summed at the operational amplifier. The example of this type of current source DAC is shown in figure to the left. In this circuit, the R2R ladder network is connected to the reference source EREF so that the individual currents that flow in vertical branches with two R resistors are given as II equals EREF over R, 1 over 2 to the power n minus 1. Each current is weighted according to the bit position it represents. The binary input controls the switches that connects the current either to ground or to the input of the amplifier. The operational amplifier sums all currents whose binary inputs are high, and that means switched on. I would like to emphasize a few important points when it comes to 4-bit switch current source DAC as shown in this picture and that you're going to build as a lab exercise. This buffer, this op-amp, has non-inverting input grounded. Because differential voltage between inverting and non-inverting is very close to zero, that means that the potential of the inverting terminal will also be close to zero. So that means that the electronic switches are either connecting branches to real ground, like in this case, or in opposite position they will connect to virtual ground, but essentially potential at the point D0, D1, D2, and D3 will not change, and that means that the current will not change that goes through those resistors. According to the expression for the current in each branch, you can find actually that there is a very simple correlation between them. For instance, I2 will be half of I3, I1 half of I2, and I0 half of I1. When a single I bit position is switched on, then individual contribution to the output voltage will be negative R times II. Now you might ask yourself, how did we derive that? It's actually very simple. This current I collects all currents in vertical branches if the switch is turned on. This current cannot flow into a buffer due to a high impedance, so it will flow through resistor R. Now if you apply Kirchhoff voltage law around this output loop, it will be consisted of two voltage drops, V out, and voltage drop across this resistor, R times II. So if we substitute II with a given expression for the current in the individual branches, you will get this expression. R and R can cancel out and you will get EREF over 2 n minus I, where n once again designates total number of bits and I is a current bit position that is turned on and whose contribution to the output voltage is VI out. Of course, if we have any combination of the switches, then we will use superposition theorem. So we will sum all currents that are switched on, which will constitute then I total current. Switched capacitor DAC presented here is a 4-bit version. It is consisted of a capacitor bank where capacitors follow binary pattern. For instance, capacitance C at the most significant bit position, then C half, C quarter, and C eighth in the last significant bit position. The last capacitor, called matching capacitor, always has a value equal to the least significant bit capacitance. Here, of course, in the case of 4-bit, it will be C8. A special B phase controls the position of the switches S3 to S0. How this B phase clock works? In the first half of the clock, all switches are connecting capacitors to common ground, thus providing discharging path, so voltage across them drops to zero. In the second half of the clock, all switches with assigned logical high connect EREF to corresponding capacitors, while others remain connected to ground. The final effect of this action that all capacitors with assigned logical 1 will be in parallel. And simple summation gives equivalent capacitance. So let's say if S3 is connected to EREF and S2 connected to EREF, they will appear to be in parallel, and then equivalent capacitance is the sum of those two. On the other hand, all capacitors in branches assigned logical 0 will also be in parallel, and their sum will be total equivalent capacitance. For instance, let's say if S1 and S2 are left connected to the ground, they will be in parallel and also will include parallel this matching capacitor. Basically, the overall result will be a series circuit shown to the left, where Cx representing the total capacitance of all branches with logical 1, and in series with the total capacitance Cy of all branches with the logical 0. Let us now review the properties of a capacitive voltage divider covered in basic electricity course. In shown series circuit, upon completion of the transition process, there will be equal electrical charge on each capacitor. So charge is a common for series circuit. Recall that correlation between capacitor charge Q and voltage across it is given with the formula Q charge equals capacitance times voltage. So if we equalize electrical charge on a capacitor Cx, you will have Cx times Vx, and it must be equal to the charge across capacitor Cy, which is Cy times Vi. Or if we substitute those two capacitors in series with the equivalent one, then the voltage Vref will appear across it, so the product Ce times Vref will designate the same charge. Of course, for the series combination of capacitors, equivalent capacitance will be given with this expression. If we solve this equation by Vx using V reference, we will come up with the expression Ce over Cx times Vref. Since Ce is given with this expression, if you substitute Ce in this expression, then Cx and Cx will cancel out, and you will get Cy over sum of all capacitance in the circuit multiplied with the total reference voltage. A similar expression you can get for Vy if you solve this first equation by Vy. So voltage across capacitor Y will be equal Cx, opposite capacitor, sum of capacitance in the circuit, multiplied with the total applied voltage Vref. This is the action of a capacitive voltage divider. Applying this expression for Vx and Vy, you can calculate actually output voltage, which is the voltage across all capacitors being connected to ground. In equivalent case, it will be Cy. So output voltage will be total equivalent voltage of the all capacitors which are switched on, divided by the sum of total capacitance in the circuit, which is always 2C. If you sum them, C, C half, C quarter, C8 plus C8, you will get a 2C. Multiply with total applied voltage is EREF. So for any input word, you might have capacitors which are in parallel, designated as Cx, and you will have capacitors which are in parallel but connected to ground, designated as Cy. This is a direct application of voltage divider. Depending on the input bit, we will have a different equivalent capacitance CEQ, and this will define different output voltages. So you can say that there is a correlation between the input word and the output analog voltage. Now, in all DACs covered so far, the reference voltage EREF can be fixed internally in integrated circuit, or it can be provided externally as a variable option. In later case, the output voltage is proportionate to the product of two variables, binary input and the analog reference voltage EREF. We call them multiplying digital to analog converters. If EREF can be either positive or negative, but the binary input represents always positive numbers, then the output of a DAC can be positive or negative, creating a bipolar output voltage. We call this DAC two-quadrant multiplier. If EREF can be both positive and negative, and the binary input represents both negative and positive numbers, then we talk about four-quadrant multiplier, having correct polarity for the output voltage for all possible combinations of the two variables. If you ask yourself how we're going to present negative numbers, negative binary inputs can be represented by using offset binary code. And here is one example which is utilizing offset from the lowest value, which in binary form will be 0, 0, 0, to the half range, so that 1, 0, 0 designate a 0 decimal number. In this case, 1, 1, 1 will designate the maximum positive number, which is 7, and 0, 0, 0 then will designate the lowest negative number, which is negative 8. Generally, calculation of the output voltage for a given binary input is given for the unipolar DAC as code, decimal code, divided 2 to the power n, where n is the number of bit, multiply with the full scale range. Full scale range. And in the case of a bipolar DAC, the output voltage is given with this expression, code, decimal code, divided with 2 to the power n, the total number of possible levels, multiply with this full scale range value, and then we will subtract half of that full scale range to get the actual analog voltage. Now a few words about digital to analog converter performance specification. When specifying digital to analog converters, there are two important properties: resolution of the converter and accuracy, where the accuracy is defined in terms of offset, gain, and nonlinearity. The resolution of a digital to analog converter is a measure of the fineness of the increments between the output values. The increment is directly dependent on the number of input bits. The most commonly available integrated circuit converters have a resolution of 8, 10, 12, or 16 bits. Some DAC specifications are quoted with reference to 1 or half of the least significant bit. The least significant bit can be seen as the increment between successive output voltages. If n-bit converter has 2n-1 such increments, then we can define least significant bit as full scale range over 2 to the power n-1. So to summarize quickly, the resolution of digital to analog converter is measure of the fineness of the increments between output values, and it can be specified as number of bits or as a reciprocal of the total number of output levels in percent, or it can be defined as the smallest increment, call it LSB, as a full scale ratio divided with total number of increments. Keep in mind that full scale range is defined as a difference between the maximum and minimum possible output voltage. The settling time of a digital to analog converter is the total time between the instant that the digital input changes and the time that the output enters a specified error band for the last time. Typical values for integrated circuit converters range between 50 nanoseconds to several microseconds. If you look at how DAC creates analog output, you will see that it's not possible to change from minimum to maximum value instantaneously. Let's say if this is the moment when we change input word from a lowest value 000, let's say, to the maximum value 1111, the output voltage will have a rise and it will take some time, Ts, which we call as a settling time, to reach the more or less stable value. Typically there will be some overshoots, undershoots, but once this output voltage enters error band, which is defined as a plus minus half of the least significant bit, so this shaded area is one increment value. Once it gets into it and doesn't go out anymore, there is no ringing outside of that error band, we assume that settling time has been completed. This settling time is one of the most critical, actually, specification when it comes to how fast converter can create output voltage. Accuracy is measured in terms of the offset error, gain error, and linearity. The offset error specifies the same DC offset for all digital data. The diagram A below shows the output voltage of a 3-bit DAC with the DC offset error. Obviously, the ideal output is a straight line starting from origin, 0, 0. As you can see, the presented offset is positive, producing conversion characteristic which has the same slope as the ideal one, but there is an DC offset, so it means it doesn't start from origin 0, 0 point. Diagram B shows the same output with the gain error. In this case, the output error increases as the digital data input increases, and this changes the slope of the characteristic. Gain error can be also either negative or positive. Once again, this would be the ideal conversion characteristics, but you can see the actual output of a DAC can either have a lower or higher value of the output voltage for the same input word. This difference is called gain error. Linearity error is the maximum deviation of the analog output from an ideal output. We said that the output is in direct proportion to the digital input, and the conversion characteristic should be a straight line drawn from 0 volts. However, this linearity error or deviation from ideal points might cause the straight line to look more like a broken line. Linearity errors can be specified as a percentage of the full scale range or in terms of the least significant bit. Differential linearity error is the difference between the ideal output increment, which is equal to the one least significant bit, and the actual increment. It can also be expressed as a percentage of the full scale range or in terms of a least significant bit. When output voltage increases with increased value of the digital input, we consider this behavior of the DAC to be monotonic, or in other words, it should be a normal behavior. However, if it happens that the output voltage decreases the value when the digital input increases, we say that the DAC is non-monotonic. Usually when there is a problem with the values of the resistor. When during the operation every input bit of the converter changes the state, we call it a major change. Let's say if we have 8-bit input word and the last value was 1000 and then 4 zeros, if this value is changed to 0111 1111, we said that this is a major change because every single bit here changed actual value. The problem is if the DAC switches open faster than they close, the DAC output will momentarily go to 0. So all inputs will go to 0 or to a full-scale value. All will get the value of 1 before they establish the new value. Each major change can cause an output glitch. Glitch area is the total area of the output glitch voltage measured in volts per second, or in case of a current glitch, ampere second. Commercial units are often equipped with the deglitchers to minimize this unwanted effect. On the right-hand side, you have a diagram which shows the actual glitch measured on commercial digital to analog converter. And it's very actually hard to get those diagrams because usually manufacturers are hiding this problem with the glitches. But this analog device integrated circuit has a specification and it shows the change from 7FF, that's in hex, to 800 hex. Obviously that's a major change. At the end, let's say a couple of words about digital to analog converter specification. The table that you see I pulled out from the analog devices site, and it lists several of integrated circuit which contain either one or four digital to analog outputs. In the first column you see the number of the outputs. That means that chip, let's say AD5735, can handle 4 outputs simultaneously, while those 5 bottom ones have only 1 output. Second row specifies the resolution in bits. You can have anything from 12, 16, 14, 10 bits, and this is of course an indication of quality of the analog output. Third column represents output type. It can be either voltage or current, or only voltage. Each of those chips, they have a specification what is the type of the output. In the next column you will recognize the range of the output voltage or currents, and more or less they are now standardized to cover the range, for instance, for currents from 0 to 20 or 0 to 24 milliamps, or from 4 milliamps to 20 milliamps. Some of them have a weird value as like AD5421, but it's a special purpose. Typically standards in industry are from 0 to 20 or from 4 to 20 milliamps. You can also get a specification of the maximum output voltage that the given chip can provide. And of course, here is maybe one of the most important parameters, which is DAC settling time. We said that's the total time it takes to provide stable output voltage after conversion. And you see that the range is around microseconds. 11, 15, 11, 50 microseconds is this one. And of course you can see right away that the cost is fairly low, because this could be considered to be a fairly slow digital to analog converter. And that would be the end of lecture 2. Thank you very much.